Check it out now, y'all.
nanoHUB-U, online instruction.
Okay, welcome back everyone. So we're on week 3 of this course. The first 3 lectures this week have been pretty mathematical. We've talked about a new approach to carrier transport that works at the ballistic limit and above the ballistic limit. We got comfortable with that in the second lecture. We applied that and developed a mathematical theory of the ballistic MOSFET in the third lecture. But it's a lot of math and equations. So what we're going to do for the rest of the week is try to get comfortable with these results. And I'd like to start in this lecture by looking a little more closely inside this ballistic MOSFET. And we'll see that there are some very interesting things going on. So just to refresh your memory about the last lecture, we developed an expression for the IV characteristic of a ballistic MOSFET. It's relatively easy to do, but a little bit of algebra, several steps. Drain current, the minus sign here is because the charge is negative, since it's due to electrons in an N-channel MOSFET. But the current scales as the width, the charge, the velocity, and then we have a voltage-dependent factor. And we can reduce that to a small voltage limit. We have an expression for the linear current. Looks a lot different from the traditional one, but that's our expression for the ballistic MOSFET. And we can apply this equation to high voltages where the exponentials become negligible, and we get a simple expression for the on current that looks actually quite similar to the traditional expression. There's a saturation voltage where we go from a linear regime to a saturated regime. In the ballistic case, that saturation voltage is very low. Just takes a couple of kT of drain voltage to make that exponential negligible, and then we're in the saturated regime. So that's the ballistic MOSFET. That's the mathematics. But let's see if we can understand a little more deeply what's happening in this ballistic MOSFET. And in particular, we'd like to look at the average velocity at the top of this barrier. That's where all the action is, and that's what we've been focusing on. So under zero bias between the drain and the source, this dashed line here is our energy band diagram. Under strong bias, we pull the Fermi level down, and we have a energy band diagram that looks like this. If we have a well-designed MOSFET, the top of the barrier stays about where it is, fixed by the gate potential. So we're interested in what is the velocity at the top of that barrier. Well, let's start with our drain current expression. The average velocity is a very simple relation. We know that current is basically charge times velocity. So if I take the current and if I divide it by minus the width times charge, that's my velocity. And we're doing the charge at the top of the barrier, so that's my velocity at the top of the barrier. Okay, so we very simply get an expression. The average velocity of electrons at the top of the barrier is the thermal velocity, this unidirectional thermal velocity that we've talked about, times this voltage factor. Okay, so we've derived that velocity. Now let's just plot it. So let's plot that average velocity at the top of the barrier versus the drain to source voltage. We'll get an expression, we'll get a characteristic that goes like this. For small drain to source voltage, the velocity will be proportional to the voltage. For large drain to source voltage, the velocity will saturate and be independent of drain voltage, and it will just saturate at this unidirectional thermal velocity. Okay. So, it's interesting, the velocity is saturating, but it's interesting where it's saturating. In the traditional velocity-saturated treatment of the MOSFET that we described in the first week, we think of velocity saturation as occurring near the drain end, where the electric field is very large. But remember, the electric field is the slope of the energy band diagram. At the top of the barrier, where we're computing the average velocity, the electric field is 0. So the velocity is indeed saturating, but it's saturating where the electric field is 0. So in one sense, the velocity saturation is similar to the traditional treatment of a MOSFET, but the physics is fundamentally different. It's obviously saturating for a different reason, because there is no scattering that can limit the velocity to this VSAT 10 to the 7th. So we'd like to understand that a little more deeply. But before I do that, I just want to mention something that we're going to come back to later. before we discuss how that velocity saturation occurs, let's look in this low voltage regime where the velocity is proportional to the voltage. Now, if I look at that and do a little bit of algebra, I can expand my exponential. E to the minus x is 1 minus x for small x, so I can make that expansion. For small x, I can just assume it's about 1 on the denominator. And I can simplify that expression to thermal velocity divided by 2 kT over q times VDS. So we see that the average velocity is indeed proportional to the voltage in that regime given by this expression. Now let me do a little more algebra. Let me divide by the length of the channel, because in this low voltage regime, the drain to source voltage divided by the channel length is just the electric field in the channel. But if I divide by the channel length, I have to multiply by the channel length. Okay. Now, why do that? Because if I look very closely at this now, I have something that has the units of centimeters per second for velocity, centimeters for channel length, and volts for kT over Q. The units are centimeters squared per volt second. That should ring a bell. Those are the units of mobility. So, but we're talking about, mobility is normally determined by scattering. The less scattering, the higher the mobility. We have a ballistic device for which there's no scattering. So mobility is a very unclear concept to use in this case. Nevertheless, I'll just make a definition. I'll define the ballistic mobility to be this expression here, this group of terms. I'll call that the ballistic mobility. And if I do that, then the average velocity in this regime is just the ballistic mobility times the electric field. All right, just what you would expect from a traditional model, although we're operating in a very untraditional regime of parameter space, no scattering at all. Okay, so that final result is surprisingly simple, and this parameter that we've introduced, the ballistic mobility, its physical significance isn't very clear, but we'll come back in a little bit and talk about it in more detail. It'll be a useful concept for us throughout the remainder of the course. Okay, now another aside before we look at the velocity saturation, I just want to remind you what a Maxwellian velocity distribution is. The probability that the energy states are occupied at the top of the barrier or anywhere else in a semiconductor is given by this Fermi function when I'm in equilibrium. If I assume Boltzmann statistics, it means that the energy states are way above the Fermi level, so I can ignore the 1, and I can simplify. My Fermi-Dirac function becomes an exponential function. Now, if I have a simple parabolic band, the energy is just the potential energy, the bottom of the conduction band, times 1/2 mv squared, kinetic energy. So I can write the probability that a state is occupied in terms of the velocity instead of the energy. And it goes as e to the minus 1/2 mv squared over kT. Okay. So if I'm talking about a MOSFET where the electrons are moving in the xy plane, then v squared is vx squared plus vy squared. So I could either think about the probability of states being occupied in terms of energy or in terms of velocity. And if you look at this velocity distribution, you can see that that looks like a Gaussian distribution. That's what we call a Maxwellian velocity distribution. If I plot that in equilibrium, so here I'm going from the x velocity to plus 10 to the 8th, minus 10 to the 8th, and the y velocity the same, you'll get a nice symmetrical Gaussian or Maxwellian velocity distribution. Every negative velocity is balanced by a positive velocity, and there's no average velocity. In a bulk semiconductor, this equilibrium velocity distribution is maintained by scattering. Electrons undergo scattering, which randomizes their velocity, and the equilibrium solution of all of that scattering between the electrons themselves and the lattice give us this equilibrium Maxwellian distribution. All right, now let's get back to this question about why does the velocity saturate? And we'll see that the physics is very simple and easy to understand. So here are some simulated energy band diagrams as we increase the drain voltage. Let's focus on the top of the barrier, and let's look at the velocity distributions at the top of the barrier. So I'll see something like this. If we begin here, if I apply 0 volts to the drain, and I just go in and look at the computed velocity distribution, it's an equilibrium Maxwellian distribution. No average velocity, no current flow, no drain to source voltage, so there shouldn't be. Now, it's a little bit different because there is no scattering inside the channel to maintain this equilibrium distribution. The way this occurs is that the scattering in the source reservoir was responsible for producing an equilibrium distribution, and the positive half of that distribution was injected into the top of the barrier. The scattering in the drain produced an equilibrium velocity distribution, and the negative half of that distribution was injected into the device. So this equilibrium distribution is really composed of an equilibrium half due to the source and an equilibrium half due to the drain. So a little bit different than it would be in the bulk. All right, now let's add a small drain to source voltage. That lowers the Fermi energy, means that there's a smaller probability that those negative velocity states at the top of the barrier will be occupied. If you want to think about it in terms of thermionic emission, there's a little bit bigger barrier now for electrons from the drain to get to the top of the barrier. Nothing has changed from the source side, so we still have the positive half coming in. So what we'll see is the positive half that came in from the source, but we see the negative velocity distribution diminishing. Now the average velocity will increase because we have more positive velocity electrons than negative velocity electrons. If I add a little bit bigger voltage, I'll get a little bit smaller negative velocity distribution, and I'll have a higher average velocity because I have an even larger percentage of positive velocity electrons. And if you go to a large voltage, there's almost no probability that the negative velocity states can be occupied. We only have the positive half. The velocity has saturated now. If we increase the drain voltage any further, we can't increase the average velocity any further because all we have is this equilibrium positive half. Its velocity for non-degenerate conditions is this unidirectional thermal velocity we've been talking about. So that's why the velocity saturates. It saturates when we only have the positive half of the velocity distribution, and we just can't get a higher velocity there. Now, I'll just mention, if you look very closely at this, at this sequence that we add increasingly higher voltages, you'll see that this positive half is bigger than the positive half that we started with. What's going on there? What's going on there is simply MOS electrostatics. The charge on the gate has to be balanced by the charge in the semiconductor channel. We haven't changed the gate voltage, so we have to have the same amount of charge under all conditions. If we've lost the negative half, it means we have to have a larger charge on the positive half to keep that charge C inversion V gate minus V threshold. And you can see that right here. You can see that the top of the barrier slowly drops down to let more positive velocity electrons in from the source such that the Poisson equation is satisfied. Okay, so that's a very inside view of what's happening when velocity saturation. This is the mechanism of velocity saturation in a ballistic MOSFET. And in a quasi-ballistic MOSFET, something very similar happens. These are the Monte Carlo simulations we've looked at earlier in the course. This is the high field region that we expect the velocity saturation to be occurring in from traditional semiconductor physics. But when we plot the average velocity versus position, we see that it doesn't saturate there. In fact, it overshoots. If we look at this point, the velocity at the top of the barrier, it's right at that knee. If I were to keep increasing the drain voltage in this particular simulation, you would see the velocity near the drain get higher and higher, even though the field is getting higher and higher. But you would see that the saturation occurs at the top of the barrier, right at that inflection point. So even when there is some scattering, the velocity saturates near the source end of the device, not near the drain end. Okay, now, if we, just to recap here, if you measure an IV characteristic and you see equally spaced steps in gate voltage under on-current conditions, high VDS, experimentalists will take that as a signature of velocity saturation. And that is indeed a signature of velocity saturation, but the saturation is not occurring in the high field region near the drain end. It's occurring over here near the source in a completely different regime. So that's a fundamentally new insight that comes from this way of looking at a MOSFET. Okay, so we have these IV characteristics. We can calculate them under ballistic conditions. The key point here is that there is a finite channel resistance, no matter how short the channel gets. We don't have a W over L here, so we don't have to worry about the current going to infinity as L is scaled towards 0. Everything just goes to the ballistic limit. And the on current gives us a nice simple expression that is, the on current is limited by the velocity that the electrons come in from the source at, the thermal injection velocity. So that's a simple expression for our ballistic on current. For Maxwell-Boltzmann statistics, the steps are Vg minus Vt to the first power. If we had fully degenerate statistics, the velocity actually increases as we get more charge in the device, and the steps become bigger, actually Vg minus Vt to the power 1.5. Typical devices will be somewhere in between, a little bit bigger than 1, but smaller than 1.5. So I want to mention, if you actually get down to looking at devices carefully, we're going to have to deal with the fact that above threshold Maxwell-Boltzmann statistics don't apply. The fully degenerate conditions, t equals 0 conditions, don't apply either. We're always in this regime where we have to deal with Fermi-Dirac integrals. And I'll just remind you, if I want to calculate the number of electrons per square centimeter with positive velocities, I'll simply do an integration of half the density of states, because only half of those states have positive velocities, times the Fermi function. And if I do that integral for Maxwell-Boltzmann statistics, I get the effective density of states divided by 2 for the positive velocities, times e to the eta F1, where eta F1 is just my normalized Fermi energy. If you do the same calculation for Fermi-Dirac statistics, we just have a more complicated integral, and the result turns out to be a Fermi-Dirac integral of order 0. For non-degenerate conditions, whenever eta F1 is much less than 0, then Fermi-Dirac integral is always reduced to exponentials, and we get the Maxwell-Boltzmann result. Okay, so we'll have to deal with Fermi-Dirac integrals of various orders that come up when we want to look at this carefully. We won't be doing a lot of this in the course, but I want to sensitize you to the fact that when you're interpreting measured data, you have to be careful about working with correct expressions with Fermi-Dirac statistics. And we mentioned this a little bit earlier in the course. There's a reference here that will basically give you everything you need to know to solve these problems with Fermi-Dirac integrals. Now, we can also take the IV characteristics that we derived, and we could redo it for Fermi-Dirac statistics. I won't go through the derivation. You know, the steps are the same as the ones we used in Maxwell-Boltzmann statistics. Basic idea is we just replace exponentials by Fermi-Dirac integrals, but different orders of Fermi-Dirac integrals come in. One of the important points to note is that the injection velocity now is not a constant number just determined by the effective mass. Now, the unidirectional thermal velocity is a label we gave to the non-degenerate velocity of the positive half of the distribution. But under degenerate conditions, that velocity depends on where the Fermi level is located. If it's higher in the band, the velocities are higher, so the average velocity of the positive velocity electrons increases. So that injection velocity actually becomes Fermi level dependent or carrier density dependent. Okay. So this is our expression. Under high drain bias, our on-current expression is just W. There's a minus sign there because the inversion charge is negative, times this injection velocity, and that injection velocity is given by this expression, and physically, it's just the positive half of that velocity distribution that was injected from the source. The average velocity of all of those positive velocity directed electrons. Right. That's what we'll call the ballistic injection velocity. That's the highest velocity that we could deduce from the measured on current. It's relatively simple to calculate. If we calculate it for parabolic bands, we get a characteristic that looks like this. It's about 1.2 times 10 to the 7th centimeters per second for silicon at room temperature, non-degenerate. Under very high carrier densities, it's some fraction of the Fermi velocity. The Fermi velocity is the velocity of electrons at the Fermi energy. But the injection velocity is the average velocity of all of the electrons below the Fermi level. So it's some fraction of the Fermi velocity. And in general, it increases with carrier density. Okay, so we can conclude. The key points of this lecture is that if you see the drain current varying approximately as Vg minus Vt to the first power, that's a signature that this transistor is velocity saturated. And every transistor I've seen, I think since about 1975, is a velocity saturated transistor. Now, so the velocity does saturate in a ballistic MOSFET. That sometimes surprises people, but we've seen that we can understand it. It saturates at the top of the barrier, where the electric field is zero, not near the drain, where the electric field is high. And the ballistic injection velocity is a key parameter, and it's not a constant parameter above threshold. It increases with increasing Fermi level or increasing inversion layer density. Okay, so we've done a couple of lectures on the ballistic MOSFET. What we want to do in the final two lectures this week is to apply this ballistic MOSFET theory to experimental devices and relate it to our traditional approach. And we'll do that in the next two lectures. Thank you.